Hello and welcome back. So in the last couple of lectures, we have discussed about fatigue and learned about different aspects of fatigue failure, including crack initiation and how the crack grows, leading to fracture. Now that we have gained some understanding about fatigue, we can go ahead and discuss about the fatigue behavior of aluminum based metal matrix composites. So when you talk about fatigue of metal matrix composites, it has been found that the fatigue life of composites is generally higher compared to the unreinforced metal. Or in other words, you can also say that the cyclic saturation stress is higher in composite. For example, if you take this composite 2219 15% TIC particles, you would find that the fatigue life of the composite would be higher, somewhere around this, compared to the unreinforced alloy. Okay, so this is under artificially aged condition, which gives rise to a cyclically stable behavior. Okay. On the other hand, if you take the same material and do the fatigue testing in artificially aged condition, then in that case it is not cyclically stable. It might show cyclic hardening or softening, but even in that case the composite shows higher fatigue life or higher saturation stress compared to the unreinforced alloy. Okay. Right, so here also you could see that the fatigue life of the composite is higher compared to the unreinforced alloy. Although the behavior of both the materials as such is same. Okay, so here for example both of them are cyclically stable, but here they are not, rather they show some kind of cyclic hardening followed by some bit of cycling softening kind of behavior. Okay, so this is under naturally aged condition where we have seen that it is not cyclically stable, and this one is in artificially aged condition. So although the fatigue lives are different, but the fatigue behavior as such, the trend as such is same for both the materials, because the matrix is same. Only the presence of these particles is making a difference in terms of the fatigue life. Okay. It has been also found that the work hardening rate of composites, particularly such discontinuously reinforced composite, is higher compared to the monolithic or the unreinforced metal, both under monotonic and cyclic loading conditions. Okay. So here is an example of this aluminium 3.5 copper composite reinforced with different fractions of silicon carbide particles. Okay, so this dashed curves that you have, this is under monotonic loading condition, and the solid curves are for cyclic loading, and different curves correspond to different fraction of silicon carbide particles, starting from 0% to 20%, and in between you have two more, 6% and 13% silicon carbide. Okay, for the cyclic loading condition, these are the curves, corresponding curves. This is for 0%, then this one is 20, and then you have 6% and 13%. So you can see that the presence of the reinforcement particles makes a difference in the work hardening rate. It increases the work hardening rate in the material. Okay, both under monotonic as well as cyclic loading conditions, as you could see from this diagram over here for this particular composite. Okay, and the work hardening increase is more pronounced under cyclic loading conditions. That can also be observed from these curves for this particular composite. Okay. So work hardening plays an important role when you talk about the effect of the reinforcement on the fatigue behavior. Okay. So first of all, we have seen that the presence of the reinforcement particles produces a large increase in the work hardening. So when you talk about the fatigue behavior of composite and the effect of the reinforcement, it is necessary to consider how the composite deforms with regard to the presence of these reinforcement particles. Okay, so it is found that there is a highly localized deformation around the particles. So if you look at the stresses at the ends or the poles of the particles is significantly higher compared to stresses away from them. So this concentration of stresses actually results from the constraint deformation of the matrix because of the significant difference in the elastic modulus between the matrix and the reinforcement. Okay. So the stress concentration results due to constraint deformation of the matrix arising because of a significant difference in the elastic modulus between the matrix and the reinforcement. All right. This constraint also leads to a triaxial state of stress and a steep stress gradient. In the matrix around the reinforcement particles. Okay. So what is the effect of this? The effect is that the deformation is highly localized. So what does it mean, this localized deformation? It means that as the material is strained, a small region around the poles of the reinforcement particles will begin to deform first. Okay. And from the continuum equations and theoretical calculations, it has been also found that for this kind of elastic, ideally plastic materials, the proportional limit is well below the flow strength of the unreinforced matrix material. Okay. So although the material begins to deform plastically in a localized manner, the majority of the composite will be still elastic. Okay. So although there is localized plastic deformation and the matrix begins to flow, but on a global scale, if you see, majority of the composite is still strained elastically. Okay. So as the strain is increased, obviously the volume of material that is plastically deforming will also increase. And eventually, because the reinforcement particles share the load, the material will reach the ultimate strength. Okay. And that is generally found to be higher compared to the unreinforced matrix. So the result of this is an increase in the measured work hardening as we have discussed. And this basically reflects in the volume of material that has been plastically deformed. Okay, so when we say that the work hardening is more, it basically refers to the volume of material which is being deformed at a particular stress. So the higher work hardening in the composite results in a higher cyclic saturation stress in the composite as mentioned before. So this is a direct result of this increased work hardening. What this essentially means is that stresses required for a certain amount of deformation are higher in the composite compared to that in the unreinforced matrix. So this is what we have seen before also for the 2219 aluminum titanium carbide composite. Although the general response to cyclic loading could be the same for both the composite as well as the unreinforced matrix material, as you could see from here or here also. Okay. Only difference that you see due to the presence of the reinforcement particles is that the stresses are higher in the composite for a given amount of plastic strain. Now, if you recall, we have also talked about stress controlled and strain controlled fatigue. This is essentially the high cycle fatigue which occurs at lower stresses and this corresponds to low cycle fatigue which occurs at higher stresses. Such conditions arise when the source of the stress is thermal in nature. Because this leaves behind some residual stresses and arises due to thermal expansion and contraction when the component is used at high temperature. And since metal matrix composites are also used in many high temperature applications, it will be good to talk about the strain controlled fatigue also. Okay. So all those things we are going to take up separately and discuss in more detail. But for the time being, you should remember that when you talk about this strain in the material, the total strain or the total strain range which is being applied, it has two components. So if epsilon t is the total strain range, it has two components. One is elastic and another is plastic. The plastic component is generally what concerns us as far as the deformation is concerned, but the elastic component is also important when you talk about the fatigue behavior of any material. Okay. So this has to be discussed as to how this plays a role in stress controlled and strain controlled fatigue. The other thing that you should remember here is that in a composite material, the stresses and strains may not be uniform and the deformation can be highly localized as we have discussed. Okay. So therefore it is important to differentiate between the average strains which represent the overall response of the composite and the local strains which arise due to the highly constrained deformation of the matrix due to the presence of the reinforcement. Okay. So when plotting the stress and strain, it may be a good idea to take the average strain, as you might have seen when we talked about the cyclic stress strain curves. We have actually considered the average strain along the x-axis. Okay. And the other thing that you should remember is the fact that the microstructural features such as particle size, volume fraction of particles, aging conditions, will also play a role on the fatigue of composites. Okay. And the other thing that you should note about fatigue of composites is the fact that the manufacturing process will also have some effect. So a process improvement can lead to an improvement in the fatigue life of composites. For example, if you take the case of this 6061 aluminum 20% alumina composite, it was found that when the process was improved over the years, the fatigue life for the same composite improved significantly. Okay. So these are the two data sets for the same composite. Okay, so these are for the same composite 6061 aluminium 20% alumina particles. Okay, so this was found when the process was improved over the years. So you can see that with process improvement, the fatigue life also improved. Okay, and metal matrix composites are often processed by casting, and a major defect in the casting is the porosity. So in castings, the casting defects such as porosities will also have a bearing on the fatigue properties of the composites, and therefore it is also important to understand the effect of such defects, and these defects should be controlled in order to get better fatigue properties in a metal matrix composite. Okay, so these are the few aspects that one should remember while talking about metal matrix composites. Okay, so before we wind up this lecture, let us take a summary. So what we have seen is that when it comes to fatigue, the fatigue life of composites is generally higher compared to that of the unreinforced matrix material. Okay, and we have also seen that the presence of the reinforcement increases the work hardening of the matrix, and this has a bearing on the plastic deformation as well as the fatigue behavior of the composite. So due to the work hardening, first of all, the stresses required for a given amount of deformation in the composite material will increase. And when it comes to cyclic loading, this also gives rise to a higher fatigue life in the composite. And then we have seen that the deformation in the matrix could be quite non-uniform. So around the particles there could be localized deformation which arises due to a significant difference in the elastic modulus between the reinforcement and the matrix. And this may also lead to a triaxial state of stress and stress gradients in the matrix near the reinforcement particles. So all these have a bearing on the fatigue property of the material. And as I said, we are going to talk about the fatigue behavior of the composite materials in more details, talking about stress controlled and also strain controlled fatigue behavior. Okay. But for now, this is all I have. So I'll stop here, but I'll see you soon again. Thank you for your attention.